Okay, this is part two of our concentrated stripping problem. In part one, we were asked to find the number of stages that we need to reduce the concentration of solute from 20% to 2% in a stream of flowing water. In part one, we ended by concluding that we needed 8 equilibrium stages in our stripper to achieve the desired purity. And at the very end, we said that 8 stages would actually overshoot the intended specification. So now the point of this video is to calculate the outlet composition of the gas. In part one, I said we could take a material and energy balances approach to find what the outlet composition of the gas is. And then I alluded to the fact that that may or may not be consistent with what we see in the separations context. So let's go to the whiteboard and work out what the concentration would be. Well, just to remind ourselves, the outlet concentration that we found was 7.8 mole fraction in the outlet air. So let's go ahead and see if that's consistent with what we see. Whiteboard. Okay, let's draw our stripper. Our inlet molar flow rate was 20 moles per minute. The concentration was 20% S, 80% water. And it was specified, we don't know what this flow rate is quite yet, but we do know that the composition is 0.02 S and the other 98% water. On the other side, we had pure air coming in at 48 moles per minute, 0% S and 100% air. And here we did not know what the outlet flow rate is. We'll call that N3, but I'll use the number that we found from last time. 0.078 was our mole fraction of S, which means that the balance, the other 92.2%, must have been the air. So going back to what we did in material and energy balances, the first thing I would do when presented with this material balance is to do a degree of freedom analysis. And as I've labeled it, I have 2 unknowns, which are N2 and N3. And I have 3 material balances because I have 3 species in the system. Now, because I'm doing an overall material balance, in other words, I'm doing a balance on this entire stripper, I can't say I have any equilibrium relationships because, remember, there are 8 stages inside. So none of the 4 streams that are coming in or out of the absorber are coming off of the same stage, so I cannot say that there are any equilibrium relationships. And 2 minus 3 is minus 1, which means I am under specified. And this should throw up a red flag for you because, remember, in material and energy balances, whenever we are under specified, that means that our information given is either contradictory or it is redundant. So in order to find out which, let's go ahead and draw some of our material balances out and we'll see if they are consistent. I have 3 material balances, so I'm going to start by writing the equations for the 3 material balances. First, I have a water balance that I can do. My water balance is the amount of water coming in, and before I start, these are all of the form in is equal to out. So water coming in is 20 times 0.8 is coming in. Coming out, I have N2 times 0.98. And that one is easy to solve for N2. If I solve for N2 here, I get 16.3 moles per minute. All right, let's go to the other side and do the air balance. Air balance is 48 times 1. Oops, what did I do? Is equal to N3 times 0.922. And similarly, I can solve this one equation, one unknown, for N3. And find that N3 in this equation is 52.1 moles per minute. Now I've got one more equation to solve. I should be able to just calculate what that number is, and if I get both sides of the equation equaling each other, I can conclude that the information I was given was redundant, not contradictory. On the other hand, if I find that the 2 sides of the equation are not equal, then I obviously have contradictory information and it cannot be so. So let's go ahead and do the solute mole balance. I have 20 moles per minute times the mole fraction, 0.2 moles per minute of solute coming in. That is going to equal N2 times 0.02 plus N3 times 0.078. And I already know what the numbers for N2 and N3 are. We just solved for those above. So I can plug those numbers in and I can work out this equation. I get 4 is equal to 4.4, which is close, but my error is about 10%. So I'm going to conclude that it's a little bit too far apart, and my conclusion is that my information is contradictory. So what went wrong here? Well, first of all, I'm underspecified, and that can't be the case. So if I go back to my Excel spreadsheet, and I look closer at the stripper that I have here, if I specify that there are 8 stages, I have to consider what, in a practical sense, what variables do I have control over and what variables do I not have control over? Well, the feed is set. I have 20 moles per minute of water at 20%. That is set. I have control over that, but you can't adjust it. On the other side, I got 48 moles per minute of air coming in. That's something else that I'm inputting, right? But over here, I specified that the outlet mole percentage was 2 mole percent. I can't specify that. If I go and operate this thing, there's no knob that I can turn that says that the outlet mole fraction has to be 0.02 mole percent. I can set this thing up with 8 stages, input the 2 streams that I can, and then whatever I get out will be a result of what happens inside. So if I remove this 0.02 as a specification and I go back to my degree of freedom analysis, I'd find that if I had one more unknown, then I could have a specified problem. So I can play with this by adjusting what X out I have. So let's say that my X out instead of 0.2 was 0.1, and we can see how the operating line would adjust in response to this. And now here I only have 2 stages that are shown, and the other 8 stages are so far too large to see in this plot. I could go the other way and say instead maybe it was 0.001, and now it's the other way. I need many more stages to reach my specification of 2 mole fraction in the outlet. And what I'm looking for here is I want 8 stages to land directly on my operating line where my X coordinate is 0.25. Just as a reminder, that happens when my inlet mole fraction is 20% and I convert that to a solute-free basis to get 0.25. All right, so one way to do this is I could guess and check using Excel. So maybe I could say it's 0.15, that's pretty close. And I find that my inlet mole fraction here is 0.22, which isn't quite the correct. So guess and check may work, or what you could do, as I love to do, is do a goal-seek analysis. So I could goal-seek. I know what I want this number to be. I want this number to be 0.25. So I'm going to go up to Data and What If Analysis to goal-seek this cell to value 0.25 by changing the outlet mole fraction and set that up to run. And now I find that if the outlet mole fraction is not 2% as specified, it's actually a little bit less than. It's 1.7 mole percent, which makes sense. Remember, I overestimated the number of stages that I needed, so my actual performance is actually going to be a little bit better than I had anticipated. Now what I have is an outlet mole fraction that is 7.2% in the air, and my outlet water is also a little bit cleaner at 1.7%. So again, this is the difference between a design type problem and a predict type problem. When you have everything that you can control specified, it's a predict type problem. So that's the end of this video. Thank you for watching.